Hello everyone, section 4.5 and 4.6, dilation, similarity, and transformations. Example 1a, find the scale factor of the dilation, then tell whether the dilation is a reduction or an enlargement. So the pre-image here is in blue. We can tell which one's the pre-image and which one's the image by the notation. P prime is over here, P is here, so this is the pre-image, this is the image. The distance from P to the center is 12 units. The distance from P prime to the center is 4 units. So we always do image over pre-image to figure out our scale factor K, which reduces down to 1/3. You can tell that it gets smaller, and this fits with the scale factor being between 0 and 1, which you hopefully have defined over here in reduction. Reduction is a similarity transformation in which the scale factor is between 0 and 1. So this one is 1/3, this is between 0 and 1, so this is a reduction. And it gets smaller. Part B, the pre-image distance from the center is 10. The image distance from the center is 25. So K is equal to 25 over 10, which reduces down to 5 over 2. This is a scale factor larger than 1, so this is an enlargement. Example 2. We're going to graph triangle PQR with these given vertices and its image after dilation with a scale factor of 3. So P is at 0, 2. Here's P. Q is at 1, 0. Here's Q. And R is at 2, 2. Here's R. So here's triangle PQR. Now we're going to do an enlargement, a scale factor of 3. So when we do that, the easiest way to do it is to take each of the vertices, P prime, and multiply them by 3. 0, 6, Q prime, 3, 0, and R prime, 6, 6, and plot these 3 points. So 6, 0, 0, 6, sorry, P prime, 3, 0, Q prime, and 6, 6, R prime, giving me triangle P, Q, R right here. And that is our dilation scale factor 3. Example 3, similar. We have triangle PQR again. We have vertices P, Q, and R given. And we're going to do the image after a dilation of scale factor of 0.5. So let me draw PQR again. Different PQR. So this time we have P is at 4, 6. Here's P. Q is at -4, 2. Here's Q. R is at 2, -6. Here's R. So this is triangle PQR. And let's find the coordinates for P prime. Multiply by 0.5, 2, 3. Q prime, -2, 1. R prime, 1, -3. Plot these 3 points, 2, 3, -2, 1, and 1, -3, giving us P prime, Q prime, R prime, and there's our new triangle. After dilation, let me show you in example 2 that if I draw from the center of dilation, which in this case is the origin, through P to P prime, through Q to Q prime, through R to R prime, you can see that the dilation is radiating out from the center. It's a little bit easier to see it in this picture. This time I'm going to draw here. This time it's shrinking in, but it's still the same radiating out or shrinking in visual. Okay, learn how to do a dilation and construction dilation by watching previous video. Example 4 is dilation in a point, or reflection in a point. So we're doing a negative scale factor this time. You want to read your definitions on what a negative scale factor is. We can still just multiply the coordinates by that negative scale factor, but what's happening is we're doing a reflection and then a rotation. We're doing the dilation and then we're doing a rotation of 180 degrees. But the easiest way to do it, again, just multiply the coordinates by the scale factor. So are we graphing F? Yep, we're graphing the original. F is at 3, 6. Here's F. G is at 3, -3. G. And H is at 6, 6. Here's H. There's our pre-image, the original triangle. And F prime is going to be -1, -2. Again, we multiply by -1/3. 3 times -3 is -1. 6 times -1/3 is -2. Continuing. G prime, -1, 1. H prime, -2, -2. When I plot these, -1, -2, here's F prime. -1, 1. Here's G prime. And -2, -2. Here's H prime. Which you can tell there's been a reduction. 1/3 is a reduction scale factor, and the whole image has rotated 180 degrees so that we have a different orientation now. All right. Example 5. Use the distance formula to show that P prime Q prime, the length of segment P prime Q prime, is equal to scale factor K, the absolute value of the scale factor K, times the length of segment PQ. Well, segment PQ has these coordinates, A, B, and C, D, so A minus C squared, A minus C squared, B minus D squared, is hopefully going to have, after we multiply by the scale factor, is going to have the exact same distance or length as P prime to Q prime, or KA minus KC squared plus KB minus KD squared. So let's find out. Segment P prime, Q prime, distance. So we know the distance formula. And we're going to have KA minus KC squared plus KB minus KD squared. I have a K in common here, so I can factor out the K, but I'm going to leave it inside of the squared, so it's K A minus C, still squared, plus, same thing here, K times B minus D, still squared. I can square the K and square the A minus C. They're multiplied together, so I can distribute the exponent through multiplication. You can't distribute the exponent through addition and subtraction, but you can distribute it through multiplication. So So I now have k squared a minus c plus k squared b minus d squared on the parentheses. Sorry. I can now factor out the k squared from this. This is something I didn't do in the answer key. Let me do it here. K squared a minus c squared plus b minus d squared close my bracket. Okay, and just like with the exponent, I have multiplication between the k squared and this long term here. I can separate the square root into the square root of this first term times the square root of the second term. So continue here. So this is now the square root of k squared times the square root a minus c squared plus b minus d squared. I can squeeze that in there. Oops. Square root of k squared is k, but because we don't know if k is positive or negative, and the end result is going to be positive, we could do absolute value. So let me slide down so I can have a little bit more space to write left to right. So absolute value of k, square root a minus c squared plus b minus d squared, all underneath the square root. And a minus c squared plus b minus d squared, this is the length of segment PQ. So we now have the absolute value of k times p, the length of segment PQ. And we have shown algebraically that these two are equal. Okay. A dilation with center AB and a scale factor k maps A to A prime, B to B prime. Find the coordinates of center A and the value of segment K, of scale factor K. So the center in this case is not the origin. It would be nice if it was, but it's not. If I do a quick sketch of these, 2, 3, 1, 2, 3, 4. Here's A. A prime is at 1, 8. 5, 6, 7, 8. Here's A prime. And B prime. So the center of dilation is somewhere on this line. I don't know where, but it's somewhere on this line. Okay, if it's an enlargement, then it's going to be back here because it's pushing A prime away. If it's a reduction, then it's over here because it's pulling A prime towards it. When I plot B to B prime, that's going to show me where it ends up being. B is at 3, 2. Here's B. And B prime is at 1, 2. Here's B prime. And again, I know the center of dilation is somewhere on this line. So where does the center of dilation have to be? The center of dilation has to be right there at 4, 2. And is it an enlargement or reduction? Well, when we go from the center to B prime, it's B prime is moving away, A prime is moving away, and when they move away, they're getting bigger. So it's an enlargement. When I find the distance from center to B, that length is 1. The distance from the center to B prime is 3. What do I multiply 1 by to get 3? My scale factor is 3. Here's example 6. Example 7. For some reason the numbering on the answer key is off. I have 2 number 5s on the answer key. That's why. number 5, number 5. And in reality, that's number 6. So this is now number 7. We're going to do a glide. We're going to do a reflection and a dilation. We're doing a composition of two transformations. We're going to reflect in the y-axis, and then we're going to do a dilation of 1/3. So this rule tells me that the center of dilation is the origin, and we're multiplying by 1/3. So the pre-image A, comma B is at 12, -6. So 12, -6. Here's point A. Point B is at 0, -3. Here's point B. And here's my segment AB. Let's do the reflection in the y-axis first. B is on the y-axis, so B prime is on the y-axis. B prime doesn't move. A is 12 units away, so I move 12 units to the other side. Here's A prime. There's the image after the reflection. Now we're going to do the dilation. So these coordinates are -12, -6, and 0, -3. So we're doing the 1/3 dilation. So now A double prime, when I multiply this by 1/3, is going to be -4, -2. -4, -2. So here's A double prime. And B double prime is going to be 0, -1. B double prime, 0, -1. And there's my final resting place for A double prime, B double prime. Describe a similar transformation that maps trapezoid WXYZ to trapezoid PQRS. How do we get from the blue to the red? Okay, so there's more than one answer here. I like to, it really doesn't matter. There's a whole bunch of possibilities. I'm going to flip it, and then I'm going to dilate it. Okay, so if I flip WXYZ in the x-axis, so I'm going to do reflection. In the x-axis. And then I'm going to, once I've done that, here's point Y, W and Z flip, X comes down here. I have this new image. I need to get Y prime to R, which would be equal to the Y double prime. So to do that, I'm going to multiply by 2. I have a length of 1. I need a length of 2. So I think if I do followed by a dilation, centered at the origin, with a scale factor of 2. That's one possibility. There are other possibilities as well. We don't have to just do that one. Example 8. We're going to prove that the square ABCD is similar to the square EFGH. I'm not going to write out the whole proof because, as you can see in the answer key, it's quite lengthy. What I will do is I'm going to walk you through what's happening here. So we're starting off knowing that AD is parallel to EH. So if I do a translation that brings A to E, so that A prime would be the same point as E, I'm just going to call it E, I'm not going to call it A prime. But moving A to E would move D over here to D prime, would move B over here to B prime, and would move C over here to C prime. Now, what it says in the answer key is that D prime is going to have to be on line EH. Why? Well, AD and EH are parallel, and translation preserves length. It preserves angles. So the pre-image and the image are parallel. So the pre-image and the second image, the in-between image, AD prime, as opposed to EH, are going to also be parallel. And the angles between them, so in other words, if I put a corresponding angle that connected from A to E, when I move A over to E, that corresponding angle is going to be the same. Well, that angle puts D prime on line EH. Translations preserve length and measure. So because it preserves length and measure, this has a length of S, this has a length of S, S, and this is 2S, this is 2S, as given to us. Okay. We also know that this is going to be a square because the pre-image was a square with all right angles. And again, translations preserve angle measures. The image is a square. And now if I do a dilation that goes E B prime gets mapped, so again, length of S to a length of 2S. If I do a dilation of scale factor 2, it's going to map B prime onto F, C prime onto G, D prime onto H. And a dilation, although it does not preserve length, it does preserve shape. It preserves angle measures. So that dilation is going to map E, B prime, C prime, D prime onto E, F, G. And if I can map one image onto the other, then they have to be congruent in the end, which means if they were congruent in the end, they had to have been similar in the beginning because the shape was preserved. Shape did not change, just the size. And that is sections 4.5 and 4.6. Thank you very much.